Normally, we turn things over to Ralph, but Ralph could not make it tonight, so we have a delegated first vice president to give the special introduction. So take it away, Jonathan.
Hi. So I have some biographical notes on our presenter this evening. Scott has been teaching physics at Lawrence Technological University since 1992, straight out of graduate school. LTU has had an Astronomy 101 course and lab for more than a decade, which reignited his interest in amateur astronomy. In late fall, he purchased a fancy telescope and apologizes for any cloudy weather that has resulted since then. Scott has always been interested in astronomical calculations, either writing code or using web resources, and he gravitated towards oddball calculations, some of which you will see this evening. So, he says that his reasoning behind presentations like the one that he's going to give is the same reason that people climb Mount Everest, because you can. So, Scott, I am a proud graduate of Lawrence Technological University, and Scott was one of the first people I met there back in 1999. So it's really been a pleasure. And I stayed.
Right.
So it's been a pleasure to have him in the club. And I did find out one of my favorite biographical facts this evening. He actually has a different tie. You may have noticed and admired his tie. He has a different tie for every teaching day of the year. So if you
some of those are the lesser ties, but I mean, I got a pretty extensive collection.
But well, I guess without further ado, take it away.
Thank you, sir. I've been teaching physics and a little bit of astronomy for decades, but I'm intimidated by the amount of astronomy knowledge in the room. So hopefully I'll show you some things that you haven't run into before. I tend to lean toward the weirder sort of calculations. I wonder if that ever happens, and how would I figure out if that ever happens? So that's what some of these are. So this was a leap year, so I couldn't resist doing some leap year stuff. So if you want to copy the talk, you don't have to go do it right now and then steal all my lines, but it's right out there. So I'll make sure I get that link out at the end too. So some of this is going to be the orbit of the Earth around the. So I've got a couple of talks that are sort of chained together. So this one is going to be talking about the Earth around the Sun, the solar day, and then leap years, and then some of these weird sort of rules that we've got for the leap year rules, and then why we have to keep adjusting. So orbit of the Sun, 365 days. Well, really, it's more 365.24219. There's solar days there. So that extra 0.24219, that's what's causing all the problems. If we could just have had the Earth to rotate on its axis and go around the same number of times, we'd be all set. So, but that darn migration of the Earth as the solar system was forming and just didn't pay attention. So we can't have the fixed number of days in the calendar unless we set up some weird days out to the 5th decimal place. We don't want to do that. So we'll skip over some of the stuff. They did the early festivals were honoring the gods, and they would try and set these festivals at certain times of the year, but then the calendar kept drifting around. Their seasons started drifting around. So they would add months in, and the rulers would just say, oh, I want a month named after me, so we're going to add one. And so you can't really just have one person, even though as powerful as they are, just sort of muck around with your calendar. It's going to cause problems later on down the road. So intercalation is adding in a day to bring the months into sync with the seasons. So if we skip up to Julius Caesar, he figured out at least we need to do an every 40-year sort of correction. But then you have 3 years of, is this the year? No, it's not the year. Is this year? No, not the year. Oh, now it's the year. And so, but every 4 years is not a permanent solution. It's not enough. But at that time, it's good enough for now. It's somebody else's problem. So that's going to be the history of, it's somebody else will figure out how to fix it. So by the 1400s, the popes were worried about Easter. Easter kept shifting around, and the vernal equinox, the spring equinox, kept shifting around. So Gregory says, okay, well, let's put in these rules. And I'm going to put out all these rules, and here's 3 different rules that come into play. And this is pretty good. Now, it's going to be somebody else's problem in a year 5,000 sort of rule. But Gregorian Reformation, they said, okay, first of all, let's not have a couple of days in October. We've got to sync up this calendar and get everything in line and add these rules to it. So we had October 4th in 1582 and then October 15th. We just skipped all those dates in the middle. So this sort of causes some problems when you're trying to do astronomical calculations, because there's these missing days. Depending on what calendrical system you're going to run into, there's this gap. And so we've got Julian system, so we can ignore the gap that's there, and we've got other ways of doing some of these calculations. But I tend to get lazy and calculate from 1600 on, because then I know where my days are. I know what the rules are from 1600 on. So, but if it's every 4 years, we add a leap day. So we add this extra day, but not if it's divisible by 100. If the year is divisible by 100. But if it is divisible by 400, yeah, go ahead and add that. So in integer sort of divisions, you say divisible by 4, yes, add it. 100, no. 400, yes. Now, does anyone remember the year 2000? There was talk about, oh, is this a double leap? Because we get the 400, but then not the 100, but then the 400. Oh, so we get a 4 and a 400 both in the year 2000. So we have 2 leap days? No, we don't have 2. You pay attention to the integer divisions. It's not a complicated sort of thing. So here's this drift. Here's the day of March is plotted on that vertical axis. So March was the vernal equinox was drifting earlier and earlier and earlier in March. Gregorian Reformation is that big spike that goes up. Now, inside here, you've actually got a little tiny, every 4 years, every 4 years, every 4 years, and so forth. And this is plotting every 200 years along here. So every 4 years, and then a 200-year gap kicks in, and then every 200 years, and so forth. So we've got these. Now, notice what happens here. Here is the 2000. This was in 2000. We said, okay, divisible by 4, yes. Divisible by 100, no. Divisible by 400, yes. So we added in a day, and that shifted it. Because look at this trend. The trend's going up. So we're overestimating or underestimating. So the trend goes up, oh, let's shift it. Trend goes up, shift it. Trend goes up, and so forth. So that's where the 4, then the 100, then the 400. So let's play around with that a little bit more. So here's this 24219. So every time we go around the sun, we don't go 365 days. We've got to go a little bit longer to get back to that spot where we're lined up in space again. And how we lined up in space is we look at our star. Outside stars are basically not moving, so we've got a system on where my angle is measured. But it takes a little bit more than a quarter, a little less than a quarter day to go around. So we said, well, let's round it off to a quarter. So there's the every 4 days. Every 4 years, we'd have to add in a day because we're undercounting. 365 undercounts how much time it takes to go around. So every 4 years, great. And we commemorated it with my brother's wedding anniversary. So it's 6th anniversary this year, but it seems like it's like 24 years. But they celebrated their 6th anniversary this year. So leap day, the 29th of February, we added on to the short month of February. And then some people see it as a free day, like, hey, you get a free day to do something different. So you get to, Big Bang Theory did a free day on one of their episodes. So that should solve the problem, right? Every 4 years, great. Problem is, 365.25 is bigger than that solar year. So now we're over-adjusting. Every 4 years, we're over-adjusting too much. If we look at the extra time that's different, we get that 0.00781 days. So 11 minutes every year is extra time by overestimating. So every 128 years, we'd add up to another day, and we'd have a problem. So they said, okay, well, let's put in a century then. Let's round it down to 100 years. And if it's divisible by 100, don't add the leap day. So 1700, nope. 18, nope. 19, all those 3 are divisible by 4, but they're also divisible by 100. So they skipped the leap day then. So 1600 was, but that's before the Gregorian Reformation. So 2000. 2000 divisible by 4, but it's divisible by 100. So we say yes 4, oh no 100. The problem was, we were now overestimating with the 4-year rule. If we go with the 100-year rule, we're underestimating. Because if we look at the 100, it's now 365.24, but that's under what the solar year is. So we underestimate with 100, and 3 minutes every year too few. We had 11 minutes too many. Now it's 3 minutes too few. So every 450 years or so, we'd end up losing a day. So we said, well, let's go 400. We'll put in the correction and say, okay, divisible by 4, yes. By 100, no. By 400, yes. So in that order, 2000 would be 4, yes, add a leap day. 100, no, don't add it. Wait, 400, yes, go ahead and add it. So we had a leap day in the year 2000. Okay, 2400 will also be one of these special cases. Now it's nice that we added a leap day in 2000 because normally we would have cut it out. But we now live in a time when we're all alive where we've got this 28-year calendar that we can play around with because day for date every 28 years is exactly the same calendar. So I'll talk about that in a second. So that should be it, right? 400, we're done. Right?
I got a question. It just runs into this. The day on the Earth is 23 hours and 56 minutes.
Good. So we've got a solar day and we've got a sidereal day. So the sidereal is, if we think of the outside walls as the stars, the background stars, so we're going to rotate on our axis a particular amount of time to go from that star back around to that star. But when I'm going around the sun, and I'm rotating on my axis the correct way, and I'm going around the sun the correct way, at least looking down from the top, the problem is I can rotate back to that star, but to come back to the sun, since I moved, when I spun on my axis, I'm also orbiting the sun. That was my sidereal time. This is my solar time. I've got to go a little bit farther along and rotate to point back to the sun. So the 24 hours exactly is the solar time. Sidereal is a little bit off, a little bit different from that. So that's that extra time. So we actually make, how many revolutions do you think we make going around the sun? 365, right, roughly?
Yeah.
We actually make 366, because if I start out here and I'm going to get dizzy if I try and do that. All the way halfway around, I'm now facing this way. I've made half of my 365, but I'm facing the other way, and then I go back. I've made a whole extra rotation in that I have moved physically around, and I've done my spinning on my axis. So we get an extra, and that's where that 4 minutes of the day sort of thing, or no, 4 seconds.
4 minutes.
4 minutes of the day. Solar day versus sidereal day. So we'll play around a little bit that. I've got a demo with my sister-in-law. So she was looking for, I had a student that was going to be coming. She keeps eyeing the door waiting for the student to show up. So I said, if he doesn't show up, you're in. So, okay, so 4, 100, 400, we're done, right? Not quite. Because we over-adjust with the 400 rule. Just barely. 26 seconds per year too much. So roughly 5,000 years, we're going to get this extra day accumulated. So this really is someone else's problem. I mean, we don't have to worry about it right now. I don't think anybody in the room is going to be hanging around checking our calendars in 3,600 years or so. So we got a couple different solutions. We could skip every 3,600 years. That needs an adjustment in 31,000 years. So that's somebody else's problem far down into the future. Or skip every 4,000. That's every 17,000 years we'd have to adjust. Or 3,000, 4,200. So what's the vote of the room? If we go 4, 100, 400, what should the next jump be? Do you like the 3,600? Do you like the 4,000? Do you like the 3,000?
Keep to the 4,000.
I like the 4,000. Not only is the 4,000 less, I mean, it's a quicker time where you have to adjust again. But the 4,000 is kind of 4, 100, 400, 4,000 seems to kind of, that flows. Now, really, they're going to have to do that once. Anyone alive is going to have to know that rule once, and that 1 year is the only time they've got to deal with it, and then another 4,000 years go by, so they're going to have to pass it on to their ancestors, say, hey, but in 4,000 years, you've got to make that change again.
Most
So,
of us will be gone by that time.
look, a couple of us might still be hanging around, so depending on how many preservatives we get with our snack food.
I think you should let the people in the future decide that,
Oh,
because they're gonna have a different need for time accuracy than we have now.
correct. I just wanted to poll the room just to kind of get a sense of which one would you pick if you could. But you're going to have to jump in your spacecraft and then wait out the universe passing and come back to be able to make that actual vote at that time. So,
If
but
on the last adjustment you were losing a day every 450 years, why not just adjust every 450 years?
but 450 years, 400, 100.
50.
So 4, but see 4, 100, 400. It runs trippingly off the tongue.
It's still only 3 numbers.
No,
from
oh,
that.
but no, but 450. 400 is such a nice 2,000, 2,400.
In that many years, most people might not be living here.
Right. I mean, we could have Mars colonized. We could have other planets that are going to have a whole different set of leap days. Mars actually does better than we do. We've got these weird rules because of that weird pesky fraction. Mars does better. They can do every 2 years have a leap day, and then they can have a calendar that can have fixed months. My very educated mother January, February, March, April. Which of them have 31 and which have 30? And Mars doesn't have to do that. They can set up a calendar that's going to be really nice and slick. And there's a bunch of different Mars calendars proposed in there. So, okay.
So, do you know how the satellites and atomic clocks, sort of what system they use to get around all this?
They're on a universal time, so they stick with whatever the universal time, and that kind of drifts a little bit. But yeah, they have to do corrections. But you can put in, but they would put in these sorts of corrections because they still have to have the right time at that moment. So they're still putting in some of these corrections, I think.
Yeah.
Yeah, they're
I think
putting
so.
all these corrections plus relativity.
Plus relativity, right. I mean, this is nothing compared to relativity. So if you can handle relativity for the GPS satellites, this is nothing. This is like 2 minutes of code versus all the relativity code. So, okay, somebody else's problem. Well, we got a 5 billion year problem coming up. So, you know, some of this stuff is trivial compared to what's going on with that. So, okay, one of the benefits is since 2000 was divisible by 400, we get a 28-year calendar, and we can only get that around one of those 2000s. So every 28 years, we've got a day-for-date exact replicate calendar, repeating calendar. So 1998, get your calendars out because they're still good, right? We've got the first internet worm, Foxtrot, the comic strip appeared. Microsoft Windows 2.1. You can mark that on. If you marked it on your calendar back then, you'd be able to see when that date was. And then Skrillex and Michael Cera, and that might be. I did this for a college audience, and they liked that line, but this may not be the right crowd for.
Skrillex is already retired.
Is he already retired? Okay. Okay, so the astronomy morsels, Jean Meus is a Belgian astronomer. That's where I get most of my code from when I'm playing around with these things. He is just terrific. If you want to do astronomy calculations, that is the guy. He is the go-to guy. Okay, 2 sunrises on Mercury. So I run into this because I do a demonstration in class on how Mercury's day is longer than its year. So it depends on how you define day and how you define year. But we're going to do that demonstration up here with my sister-in-law in just a few minutes. But also, as I was running into that, I ran into that Mercury can have 2 sunrises. So let's play around with this. So the Earth we know. So here's the sun in the middle, and if I'm the Earth, I rotate on the axis roughly 360 degrees per day, right? We're doing 1 day around, and I'm going basically 360 degrees in that 1 day. So I've got I'm going to call that the W axis, the omega, the angular velocity, would be a angular frequency, would be on my axis, roughly 360 degrees per day. That's pretty fast. So here's the sun, and I go around, there's my 360 degrees in that 1 day, and then I'm moving slightly around the sun, so there's my next 360 and next 360 and so forth. But I make many axial turns for every time I go around the sun. Okay, and I'm going to do my T-Rex jazz hands, right? So that's T-Rex if they did jazz hands. So here's my eastern horizon, here's my western horizon. So as I rotate, there's the sun rises in the east, the sun sets in the west. Right, from my perspective. The sun always rises in the east and sets in the west for the Earth because we rotate so quickly on our axis. If we didn't rotate on the axis, we did not turn on the axis, if I still orbited the sun but did not turn on the axis, then I would get a sun, there's midnight, right, sun's behind me. Here is now the sun rising on my western sky, and then here's high noon, and then here's the sun setting in the eastern sky. So my orbit is causing a sunrise in the west, sunrise in the east, or sets in the west. I can't say it because we're so used to saying it the right way. It's sun rises in the west and sets in the east. If it's just the orbit effect. But my rotation on my axis says, no, sun rises in the east, sets in the west. Since the orbit, or the axis is so fast compared to the orbit, rise in the east wins, right? But what if it weren't? What if we've got something where the orbit time is faster than what the axial time is? Okay, so we get if we did the orbit one, we get a west to east. So the W for the orbit for us and for any planet that does what we do, go around the sun in that same way, it's a west to east motion. On the axis is an east to west motion. Our axial frequency, our axial speed is so fast, we get east to west. But what if we didn't, right? I hate to quote the core, because that was one of their things in the core, but what if you could? So it's a great movie to do bad science calculations. But okay, so if the rate of the orbit is bigger than the axial rate, then the sun would move differently in the sky. Okay. All the planets have elliptical orbits. So I can't just say, oh, what's the W for the orbit for that particular planet? Because sometimes when they're closer or farther away, they're going to have a different time that they're going. How much of an angle around the sun are they going in the same amount of time? It changes because if they're closer, they're going faster. If they're farther away, they're going slower. So a perihelion, when you're close to the star, Helios star, or sun. So if you're close, then the W orbit's going to be a higher value. If you're far away, aphelion, then it's a smaller value. Okay, so let's call them per and ap. And both of those are the orbit ones. Because the axial one basically is fixed for the planets, right? For each individual planet, their axial rate is basically fixed. But the orbit rate changes if I'm closer to the star, if I'm farther away from the star. Okay, so now, if that perihelion or aphelion is bigger than the axial rate, then we get a west to east. What happens if the axis rate is in between those two? So if perihelion it's faster, but aphelion it's slower, there's the axial rate in the middle, that's the sweet spot. So here's a big giant data chart. Here's just all the planets, even counting Pluto. Here's the eccentricity, here's how much of a circle it is. So Earth is here. Yeah, Earth is pretty good for circular orbit, but Venus is really nicely circular compared to the other ones. Here's Pluto way out here. Mercury's 0.2, that's pretty elliptical, it's pretty stretched. What's that?
It's not a planet.
Shh. Mercury's not a planet or Pluto?
Pluto.
Pluto. Okay, here's objects in the solar system. I'll make a correction for planets up there.
No,
This
I'm
is
saying
old chart.
Mercury, I'm taking the IAU even further. I'm saying
Oh.
Mercury shouldn't count.
Okay.
Needs to settle down.
Okay, yeah. Cool it back there. I'll set my sister-in-law on you back there. Okay, so we have an orbit period. How long does it take to go around the star? We've got the average of how many degrees per day for the orbit. We've got an axial period. Now look at Venus. Venus is weird. It's got a negative number for that. Venus rotates on its axis backwards compared to the way it's going around the sun. It's got a retrograde axial rotation. So that's going to throw us off because that degree per day for the axis is negative. It's not. Venus is not going to have. Is not going to be in our game here. But look at what's going on with Mercury. Because it's so eccentric, we get two different values here. Perihelion is moving pretty quickly around the sun. Aphelion moving pretty slowly. But this number is bigger than this number. Here's the axial number. Now let's look at the Earth. Here's the Earth. 360 degrees per day, basically. We're only 1 degree per day around, right? Because we go all the way around 365 days to get around. So this is huge. I've got an east to west, east to west. If this column is bigger than this column, east to west, east to west, east to west, the normal way. But this column is bigger than this column. So for Mercury, near its perihelion, it's actually going faster around the sun to create that, hey, let's have the, how did I do that? Hey, let's have the sun rise in the west and then set in the east before it can get its turn, its axial turn to get the east to west sort of rise.
That's,
Pretty slick.
yes.
Okay, so plotting this, there's our spike of the axial, right? And so for all those outside planets there, forget it. They're spinning too fast on their axis. All the sunrises, forget Venus. I didn't put Venus on there yet. All the sunrises are east to west for all the outer planets. If we look at Mercury, there's Venus actual. It's going backwards. But Venus prograde, even if Venus were rotating on its axis the, quote, normal way, it still wouldn't work. But look at Mercury. Mercury's got that spike where its blue perihelion is bigger than the axial rate, and that's less than the aphelion. I mean, the aphelion is less than that. So it's right in the middle. So if it's going close to the sun, it's actually moving around the sun fast enough that it causes the west to east as opposed to the east to west.
Very cool.
That's interesting. Okay. So, as it approaches that perihelion, the sun, wherever the sun is in the sky, the sun would basically stop in the sky, reverse a little bit, and then go forward again. So it's almost like a retrograde the way Mars does.
Yep.
If it happens around the sunrise time, double sunrise, right? We can have the sun rise and then set and then rise again. So let's plot the sunrise. Let's do it right near perihelion and pretend that it's sunrise time. Let's plot the angle up from the center of the sun above the horizon, and we'll see it come up over the horizon, go down, and come up. So here's this. Here's a great plot. Ready for this? Ta-da! See how convincing that is? The angle below the horizon comes up, and oh, should I zoom in? Maybe I should zoom in a little bit so you can see it. Okay. Ah, there we go. So below the horizon, as we're getting close to perihelion, we come up above the horizon, set. Again, here's a sunset. So here's sunrise, sunset, then sunrise again. So there's the second sunrise. Now, what would be nice on this graph is to see how big is the star, right? How big, how much of the sun is actually coming up. So it's kind of a cheat because looking at how big the sun is at that moment in the time, we get this. There's where the sun, it doesn't quite lift all the way off the horizon, but there's a difference in terms of when we say sunrise, don't we As astronomers, don't we mean this, the limb of the sun just touches above the horizon? Okay, so technically that is a sunrise. It didn't come all the way up. The center gets above, but the whole body of the sun doesn't get above the horizon. And then it sets then and goes up again. So somewhere way back when I first did this talk, somewhere out on the interwebs, there was a video that had, somebody did an animation of this, where they animated from using the astronomy software. And so I grabbed that animation, I still have it. So here's one of them. And this will show, so remember what this said, this showed the just barely above but not completely off the horizon and come back down. I think that's my green grass, right? That's the green line is the horizon, that's the grass on Mercury, I guess. Or, okay, so let's try this. This will rise, not quite all the way, set back again, and then rise again. Now notice all that, what's all that star stuff going? We're whipping around the sun, relatively speaking, with Mercury. So that's all the star field behind. As we're only focused on the sun, we're coming around this way, so all those background stars are whipping past us. Let's zoom in a little bit. I got another slide that zooms in a little bit better. So this pretty much matches the graph. It comes up, just over the center, goes back down again, completely under, and then back up again.
What is the time sequence?
I don't remember. So, oh wait, if I go back to the graph, it's got the days on it. So this is only a certain number of days. This is days from perihelion. So this is on the order of a 2-week period.
2 weeks.
They have a very, very long sunrise,
Okay.
right? This is a couple weeks of sunrise. So you would notice it. You'd say, wasn't the sun higher yesterday? Now it's, wait, where'd the sun go? I thought it was rising and now it's not rising anymore, so. Okay.
Initial question, what planet was that in the animation? Was that Earth or Venus?
That was from Mercury. From the surface.
I mean, there's a planet in the star field.
Oh, you know what? I don't know.
But
So in
hit
this,
again and see if anybody else spots it.
Yeah.
was it in this one or is it in the other?
There,
There. Oh, there's both of them. Okay, so that was presumably Earth and Venus.
cool.
Okay, wait. Now I got to see. Now I missed it.
And actually, I think Jupiter was in there too.
Oh, that's got all the lettering. So let me go back to the. If you can see it in the zoom.
Yeah.
Mhm.
Oh, there it is.
Yeah,
So that
both
one
of
right
them.
there.
There were
Yeah.
two of them.
Two of them.
Yep, those two. There were two.
Okay, so watch this region of the sky here. All those stars are going north, and one of them is going to come south. There.
There's one, there's
There's
the
another
other.
one. Oh yeah.
I think it was Venus first and then.
Nice.
Yep.
I think this
Yep.
was done with Celestia, which is one of these astronomy software animations. So very nice. Okay.
Very cool.
Okay. So will Mercury always do this? Well, the eccentricity varies. It's got all these planets are pulling at it, and that pesky GR, the general relativity, because it's so close to the sun. So right now it's 0.206 for its eccentricity. If it's exactly 0.191, so it varies between 0.12 and 0.23. So if it's exactly that, the sun would just stop and then go forward again. It would sort of pause. It wouldn't back up and go forward. But the eccentricity is on the rise. So we've got plenty of years left for Mercury. So we've got to get over there to be able to set up a base to watch this. But, okay, and again, there's the astronomy morsels from Gene Meas. He is the guy, and some guy named Harry on Celestia did the animation for that. Way back in the mists of, I tried to search on the internet, I didn't find it, so. Okay, now I need a volunteer from the audience. Anyone at all, anyone, a volunteer, Mary? Mary, come on. Okay, so we want to do the day longer than a year. So Mercury's day is longer than its year. So what we're going to do is, Mercury orbits the sun, goes around the sun every 87.98. Let's round it to 90 just to make it easier. Mercury's orbit on its axis, period on its axis, is 58. Let's round it to 60. So every 60 days, Mercury rotates based on the background stars, one time on its axis. Every 90 days, it goes one time around, meaning if I'm lined up with a star over there, I come around the sun, I'm lined up with that same star. So now what we want to do is watch what time of day is it for Mary Mercury here. And so we're going to set it up so, what if I did every 15 days, right? If we look at 60 days, Mercury on the axis. So every 15 days, there's 4 of those 15-day periods on the axis. So that could be the 4 walls, right? Face the wall, 15 days later, face a new wall, because it'd be 90 degrees, 90 degrees, 90 degrees, one time around on the axis. Every 15 days would be basically 1/6 of the way around the sun. So it's 60 degrees. So I've got blue marks on the floor here, every 60 degrees. So there's 6 of these blue marks around. So all you have to do is set up Mary Mercury, and she's going to do her T-Rex jazz hands, right? Okay. So there's her eastern hand, right? There's her western hand. So we can watch for the sunrise. Now we're going to see double sunrise on this one, but I don't want to complicate it for Mary. So, but eastern. So now she's doing sign language. So there's E for eastern, and there's W for western. So there's the eastern hand, western hand. Okay. So right now, what time of day is it for Mary? If she's facing this way, she's facing this wall. We're going to start with high noon. Let's call this west over here. Okay. If that's west, this is north. That's south. That's east. Just call it that for the room. So if she's facing here, there's the sun. What time of day? High noon, right? Okay. So what I'm going to do is I'm going to shift the slide so that we've got, so there's high noon. You're facing that way, right? Okay. So every time she goes to a new step here, that's 15 days, she's going to rotate. Now, she is going this way around, right? Looking down from the top, it's counterclockwise. On her axis, she wants to rotate also counterclockwise. So she's facing west, then she's going to face south, then east, then north, right? So you just turn one wall that way, one wall that way, and so forth. So jump to that spot. So she's there, she jumps to that spot, face the new wall. Okay, what time of day?
5 days.
Yeah, so here would be sunset over here, so it's noon, it's, you know, middle of the afternoon or so. Okay, one more jump. Face that wall. Okay, sun still hasn't set. Right? Still above her horizon. It's above her western horizon. Okay, so one more jump. Now, what time of day is it for her? Sun is on her western sunset, right? It's just starting to set. She is now gone, how many days was that? She's facing 15, 30, 40, 45 days. 45 days for the sun to go from high noon to sunset. Okay, so next one. And that way, so she's facing this way. First axis rotation. She started out facing this wall, right? So that's one sidereal day. She's rotated once on her axis. The sun has just barely set though. Okay, one more. Over there, yeah. That way, okay. So sun is still setting, right? It's, I mean, setting, it's below, but it's still not even midnight for her. Okay, again. Here's her first year. She's gone 1 year around, right? She's back to where she started in the room. What time is it though? Midnight, right? So she went 1 year around. She only went half a day, half a solar day, right? So one more. You got to get back to high noon again. You haven't gotten to high noon. Okay. So it's beyond midnight, right? The sun's starting to now rise, sort of, on her eastern. Okay. So keep going. Here's her second axis rotation. She's now rotated twice on her own axis because she's facing me again. Hi, Mary. So she's facing me. Second axis rotation on her own axis. She's gone around one full time around the sun. She's still not yet to a full solar day. Okay? There, what time of day? Sunrise. Finally, we get the sunrise again. This is now the second, into the second day. So go ahead, one more. Okay, so where am I? That's this. Oh, there, yep, that's good.
9 o'clock in the morning.
Okay, so now it's, yeah, so the sun has risen and it's now up. It's not yet to high noon though. Okay, one more. Not yet. Whoops, wait, yeah, there you go, okay. So the sun's higher in the sky but not yet to high noon. Okay, one more. There we go, second orbit year. She's gone orbiting around twice. Third axis rotation, she's rotated 3 times on her own axis. 2 times around the sun to get to 1 noon to noon. So 1 day, 1 noon to noon, is 2 years. 2 years on Mercury in terms of 2 trips around the sun, 3 trips on her own axis just to get that 1 noon to noon solar day. It's a complicated planet. Yeah, that's going to be, so, and it took, so how many days did it take? It took 180 days just to go 1 solar day, 1 high noon to high noon. Good luck with your calendar system and your hour system for that period.
Scott, how does it stay on the same ellipse for all of its orbits?
No. Mercury precesses. So, thank you, Mary. Okay. So, most of the other planets, they've got little precessions, but Mercury's got a relatively, everything's relative, relatively extensive precession, somewhat due to the other planets, but also because it's so close to the sun. So its perihelion, its closest approach, drifts around. And we tried to account for it with all the Kepler stuff, all the planet stuff, couldn't quite come up with this extra little bit. Einstein walks in and says, hey, yeah, general relativity, he said in a German accent, but he said general relativity, that's going to get you that extra missing piece. It locks in beautifully at that point. So the perihelion location is drifting around, but over a relatively long period of time. It's not, this kind of model and the double sunset sort of thing would still sort of work over the next, as long as we're worrying about, we haven't worried about our, is it 3,000 years or 4,500 years, or we can still do this. Okay. Okay, so retrogrades, Marvin the Martian, and the universe, oh my. Every time I put three things together, I get the oh my from lions, tigers, and bears in my head. So my students are tired of that. Okay, all the planets go around the sun basically the same direction, right? They're all, if we look down from the top, it's all counterclockwise. So we'll define that reference as the Earth-Sun plane. We call that the ecliptic plane. All the planets are relatively tilted a little bit, not too much, but a little bit. Venus is a tilt of about 3 degrees. So hold on to that information. So Venus' orbit tilt about 3 degrees. Okay. So the retrograde motion is Mars is in opposition, right? When Mars is in opposition, we're coming around. So let's say Mars is, so my father-in-law out there is Mars. So wave, there's Mars. Okay. So as the Earth comes around, Mars is going around the sun, but as the Earth comes around, Earth catches up, passes Mars. So if I'm looking at Mars in the sky, Mars is plodding along against those background stars. Once I get into opposition, Mars appears to back up and then go forward again. Now the ancients looked at this and said, well, we love circles because circles are perfect, but that's weird what he's doing with it going backwards in the sky, so let's add another circle on, because circles are so great, let's add another circle. So there's the epicycles. Kepler comes along, has his elliptical orbits, and says, hey, wait a minute, if we orbit this thing instead of everybody orbiting us, we can explain this retrograde, no problem. This is a piece of cake. So I had a retrograde motion for Mars, and I made this with, I think it's not Heavens Above, what's the Formulab? Formulab used to have software that you could run, Home Planet. Home Planet was the software you'd run on the PC. So here's Mars coming in, and Mars comes in, backs up in the sky, and goes forward again. So I'll run again. There's the moon going by, you can see the moon. So there's Mars coming in, day by day by day it's going through. Now this is back in 2001. So Mars backs up relative to the background stars. So if you look every night, you sketch it every night, take a picture. Back up, and now it's finally going prograde again. Okay. So the first thing I did when I did this was I'm watching Mars and I'm plotting it out for my students, and then I said, hey, look at Pluto. It's like looking at the double sunrise, and Jonathan says, hey, you got 2 other planets in there. And I said, look at Pluto. Oh, Pluto's doing retrograde too. Any of the outer planets, Pluto's now basically in opposition because it's there in the sky here, so it must be out there somewhere. Mars is here. So if I'm in opposition with Mars, here's the sun, here's me, there's Mars, Pluto's sitting out there. So if Mars is going to go in opposition, so is Pluto. So Pluto's got a little bit of a jog. It's coming in and then going that way and coming back again. It doesn't make as much of a change because it's way far out there. And we're only looking at a certain number of days here. So I mentioned this to my class, and the student that was supposed to come here, that would have saved Mary, says, hey, we're in retrograde now, right? Mars is going into retrograde. I said, oh, shoot, I should have known that. So I'm going to go talk to astronomers. I kind of should have had that information. In fact, I even pasted in, oh wait, hold on to that thought, that I didn't know that Mars was in retrograde now. So the shapes of these retrograde loops, if we looked at this and plotted out this shape, this comes back here, and then goes forward, and then comes, so when it comes in here. I'm really good at following this planet. And then backs up. So you get some sort of zigzaggy shape. It's kind of a better, more open curve, but that seems to come in and relatively flat, go back out again. So there's a particular shape to that retrograde curve. So how does the shapes change as Mars goes into opposition? It's got different times where as Mars goes around, we lap it, we come back around, Mars is moved. So now Mars goes into opposition over there. And then it's over there, and then it's over there. And then we come around, Mars has moved it along. So all these opposition points spin around the dot. Okay, so as we go through, it depends on what kind of shapes you've got. If Mars happens to be moving to its upper, above the plane of the solar system, then you get an upper loop, and it comes back down again. Or if it's going below the plane of the solar system, if it's got to its lowest point when it happens to be in opposition, then you get the downward loop like that. Or if it's passing through the node, so if here's the ecliptic plane, the Earth-Sun plane, and if Mars happens to be going down from above, when it's in opposition, it does a zigzag and drops below. Or if it's coming up on the other side here, it's rising off the plane, then you get the zigzag that way. If you get in between those, then you get these crazy sort of shapes. So here's the June 2001 sort of shape down here. That's basically what we saw in the sky. It went this way, came over, went back. And we're plotting now, here's Mars on the outside loop, here's the Earth. So the Earth stays in the plane, because that's what we define the plane. We're the ones making the names. So we say, we're the plane. Everybody else is tilted relative to us. If Mars wants to come down and shift it and make it their plane, fine, but they've got to come down and talk to us. So here is above and below the plane. So here's the one that's above. So Mars is the highest off the plane here. Here's the lowest below the plane. There's the low retrograde sort of shape to it. And so these shapes, you can see them morph. They go from here, curly Q, there's a cusp sort of thing, then it opens up to the Z, then there's a cusp the other way, then it's a curly Q, then it's a low, and so forth. Shoots around. So June 2001, that's that shape that I had in my animation. So my students said, oh yeah, Mars is going into retrograde now. Ooh, I'm going to go talk to astronomers. I should have known that. I even pasted in this chart that shows all these oppositions and shows all the shapes. And right here here's our 2016, it's going in opposition. Luckily, it looks really close to what I just showed you. So I, of course, thought this through and said, I can use my old animation because it's pretty close to, come back, it's pretty close to that shape because I'm looking at 10 is right down here. Are you really going to be able to tell the difference between that and that? Of course not. It's basically the same. But look at this. This is June. The other one is listed as late May. Late May, June, here's the year going around, right? So we happen to be, now what is this, 15 years later, roughly in the same spot for an opposition, so we get roughly the same retrograde shape. So I got lucky on that, because he said, yeah, you should have thought of that before you go talk to the astronomers. Okay, so there's a great transit book by guess who? Jean Meus, the Belgian astronomer. So, okay, Marvin. Why is Marvin so upset with the Earth? Who knows why Marvin's angry with the Earth? He wants to blow up the Earth.
Blocking his view. That duck has something to do with it.
Now, it doesn't. Bugs Bunny. He's got.
Oh, yeah, Derek Duck was on.
Yeah. He's got Canine as his sidekick sort of thing. Jonathan, why does Mars want to
I was
blow?
going to say Bugs Bunny.
No, it's not Bugs Bunny.
He's blocking his view of Venus.
Blocking his view of Venus. So we have to make sure we follow this line of reasoning here.
Something tells me I should have stood in bed. Where the heck am I, anyways? Well, wherever it is, I don't like it, and I'm getting out of here. Hey, maybe that character wearing a spittoon can help me.
At last, after 2,000 years of work, the Illudium Q-36 explosive space modulator.
Pardon me, sir, but could you...
At long last, my dream come true.
Hey, Doc, wait! I want to ask you something. Pardon me, Doc, but could you rent me a U-Drive flying saucer? I've got to get back to the Earth.
The Earth? Oh, the Earth will be gone in just a few seconds.
Oh, well, don't bother then. No point in wasting money on a flying saucer when the Earth's not gonna... Pardon me again, Doc, but just what did you mean by that crack about the Earth being gone?
Oh, I'm going to blow it up. It obstructs my view of Venus.
It does? That's a shame.
Where's the kaboom? There was supposed to be an earth-shattering kaboom! The Illudium Q-36 explosive space modulator! That creature has stolen the space modulator! Delays.
Okay, so imagine the hilarity that ensues with the just add water to 10,000 instant Martians. So we don't have time to play that clip, but so that was his beef. He was upset because it blocks his view of Venus. So I would have seen this when I was a kid, and my brother and I would have made the Marvin the Martian voice and annoyed each other, and my sister. And it wasn't until I got to the point where I could start doing some of these calculations that it stuck in the back of my head. How often does that happen? That the Earth is in the way between Mars and Venus? because we're in the plane, right? We defined our plane this way. But Mars is sometimes above the plane and Venus is sometimes below the plane. But how often do we actually get in the line of sight so we block that view of Venus? Of course I had to do that calculation. Now I did this a while back, and I really should go back and recheck this calculation, but I did try with some astronomy software. But at the time when I was doing the calculation, I had an old laptop, and it was up in the Adirondacks, upstate New York, and so I was in this little tiny cabin. Here's this laptop. I had it propped up on pop bottle caps to let the air cool it, because I was running it for literally 2 days straight just to get this one calculation in there. I mean, the final calculation for this. So, the conditions for blocking. There's our Earth, right? Here is now our Mars is out here, and here's Venus in here. So, if Mars is way above and Venus is way above, well, they just shoot over the top. He can see Venus, no problem. If Mars is way below and Venus is way below, they can see, no problem. It's when they're starting to cross, like I'm above and you're below, and Earth's right there in the freaking middle, right on the ecliptic plane. So here is the spot. So what I did was I said, and there's many different ways of doing this. Mine was just a brute force. I had the ability to calculate where is Mars, where is Venus, where is Earth. And let's draw a line between between Mars and Venus, and say where does that punch into the ecliptic plane? Where is that line? It's up here, it's down here. Where does it punch through? Here's all the dots where it punches through. Now, a bunch of these, Earth's never going to be here. If Earth's here, we're in trouble. Right? If Earth's out here, we're in trouble too. So Earth's got to stay on that blue band. So here are the times that I have to check. And it's really a window of time here and a window of time there. So this is sort of late, let's see, this is, I got to remember how I oriented this. One of these I know is November, and you'll see why in a second. And the other is 6 months away from that. So Venus is up and Mars is below, or Venus is below and Mars is up. That's the times we're looking at. If they're right on the axis, if they're right on their nodes, we're not anywhere close enough. So it's got to be slightly above, slightly below. Okay, so I crunched the numbers, and I went from the year 1000 to 3000, because Marvin says 2,000 years of whatever, so I figured I'll run the whole 2,000-year gambit there. 1,000 years to 3,000 years. How many times do you think it comes up?
12.
12.
0.
0. 0? 12 and 0, those are odd. I mean, 12 months, I can see that 0 is a logical sort of. One time. There it is. 2746, that's when that's going to happen. We are going to be obstructing the view of Venus from Mars, so our Martian colonies, if we're now off the surface of the Earth, our Martian colonies are going to go, oh, I was just going to look at Venus tonight through my telescope, freaking Earth is there. Let's hope they don't have yeah, the space modulator. I was trying to think of the U-236 is exploding space modulator. So let's hope they don't have one of those, because that time, and roughly 7:45 in the evening. So
how long would that occultation?
Yeah, the occultation, so I tried it with some astronomy software. I got to try it again, because this was pretty good. I got to check my numbers just to make sure, but it's not that long. It's a very brief window. So Marvin's really a little pushing it here to blow up the entire Earth. I think he's just got to decaffeinate, because that's a little too much.
I'm going to be 770 years old then.
There you go. What a way to celebrate it is not see Earth, right? Or not see Venus.
And really, who would rather look at Venus than Earth?
I'm just saying, that's Marvin. Marvin's got his own deal going.
So how often does that happen?
So in that 2,000-year range, it happened that one time. We'd have to check to see when does it happen again after that. So I didn't run those numbers.
It would probably last for a few hours, maybe.
I don't think it even was well, maybe a few hours. Right. So, but the next time, then I got to play around with my software, because then it gets a little extreme to go 3,000, 4,000 years out, trying to plan where the planets are based on the code we've got. So, yeah. Okay, so but at least within this window of when Marvin really could complain, it's one time out of a 2,000-year window, I think.
Now, what would you have done if you would have gotten the answer 0? Would you say I have to go back and have a larger window?
No, I probably would. I couldn't imagine that it only came up once. I kept thinking, this got to come up more often than that. You know, it just seems like the lining up of these planets and it's not even lining up with the sun. It's just lining up 3 dots in space. How can this not show up more often? And so I was thrilled to get 1, because I thought if I get 0, something's wrong with my code.
Also, doesn't it have to happen during the middle of the day?
Not necessarily, right? It depends on where we are in the day, where we're rotating on the day.
Oh, yeah.
Right.
could the Earth occultate Venus behind us?
It's not lined up with the sun. So they could be in a line out here.
Okay.
All I'm doing is I'm trying to look at Venus and Earth's in the way.
But from the perspective of Mars.
Mars, right. Mars is trying to look at Venus, but Earth's stuck in the way.
Right. Oh.
Right. And I don't have to line up with the sun. It's not going to line up with the
Well, but
sun.
it would
Because we
still,
don't have time zones on Mars.
but the sun would still be up.
Oh, I see what you mean. From the Martian perspective,
Right.
yeah, it'd
Yeah.
be daytime,
Yeah.
right. But you're looking offset from. Yeah. So yeah, that is okay. So I didn't. So right now, here's my next. Every time I gotta talk like this, is like, oh crap, that's the next thing I gotta do. So now I gotta find out. Well, where are they? What's that line look like? I didn't even plot out where they are in space when that happens. So is it really close to the sun, and then you've got to have a solar filter, but then you're not going to see the Earth or Venus if you got your solar filter blocking it. So great, now I got to figure out where the stupid planets are. At least I showed there was one occultation, but
What about
okay, Mary, write that down. That's my next calculation.
Scott?
Isn't
Got about 10 minutes.
Isn't the Earth and Venus in a resonance orbit? Aren't they in resonance?
Yeah. Oh, so wait. Right. Thank you. Excellent. What a timing. So here's a thing that's out on the internet. And they show this, and here's Earth and Venus. And roughly every 13 orbits for Venus is 8 orbits for Earth. And so they make this little pretty picture. And I looked at this, as I do often with internet stuff, and say, yeah, I don't really think that's, look how pretty that is. A nice 5-fold petal pattern, exactly symmetric. And I said, I know, come on, hang on, guys. Because this is circular. They're doing circular orbits, exact circular orbits, and they're drawing out this thing. And so I thought, well, it can't look like this. It's from the internet. I mean, how accurate can it be? So I did a calculation, the exact numbers that I had before. That's not bad, right? There's a 5-petal. Now what I did was I superimposed the circular, from the sun, I did circular radii out. So you can see that this one is not quite at that edge. This one is right up to the edge. This one's over that edge. So it's not symmetric the way the other one was, but it's pretty darn close. Right? It's not too bad. You can see that these shapes are not exactly the same petal shape, but it's really close to what that other one was. It's not a bad resonance in terms of the 8 and the 13.
There's your epicycles.
What's that?
There's your epicycles.
There's the epicycles, right. So if I rotated that other original internet image, that's a pretty close matchup, but you can see where this is all perfect. All of these intersection things look identical, and these look kind of messy. Here's one. This is grouped in here, but it's not. It's messy there. It's messy there. So the real planet lineups don't fit that petal pattern, but come darn close. So
It's purely due to the elliptic.
exactly, the elliptic, right, exactly. Yep.
But the really weird thing is that Venus and Earth are tightly locked.
Right.
They're not tightly locked, but nevertheless.
But there's a resonance to them, right. This is like the Trojan asteroid, well, the Trojans are a different reason. This is like the Kirkwood gaps in the asteroid belt, where they're tightly locked with Jupiter. You get a 2-to-1 ratio, you get a 3-to-2 ratio, and so forth, and there's these gaps in the asteroid belt. But here's my question to you. This is the question I'll leave you with. So it can't be as simple as 13 minus 8 equals 5. Right?
Right.
But why 5? Why the 5-fold?
Is it part of the Fibonacci sequence?
That's kind of weird.
5, 8, 13.
Yeah, but why a 5-fold? Just because you got the 8 and the 13 that line up and repeat, why is there now a 5-fold pattern? I don't know the answer to that. So that's the question I'm going to leave you with. But the first thing I said was 5 was, oh, 8 minus, or 13 minus 8, that's 5. That can't be it. There's got to be some other, but then I was trying to think of least common multiple sort of thing of how many times if you go 13 times around for Venus and 8 times around, but that's out to, what's that, 13, 8, what's 13 times 8? Whatever that is for how many years till the whole thing repeats. That's not 5, so, right. So where's the 5-fold symmetry come from? Or semi-symmetry?
104.
Well, it looks like.
So I guess what I should try is, this is 8 and 13, if I did, this was circular orbit, so that's easy to program. So I could program a 7 and 13 and see if I get 6-fold symmetry.
Right.
Mary, write that
There
down.
are 85 different combinations. Again, you've got your 13 times 8.
Right.
But you're going to only have 5 where they're gonna line up a particular way.
Why though? Is that a synodic period? Is that a, well no, it's not synodic. Synodic would be when they both line up with the sun again. The Mars in opposition is a synodic period of, it's Earth and the sun and Mars, oh wait, Earth here, sun there, Mars there. So that the next time that lines up, that's called a synodic. The next time that lines up. But I'm not sure where the 5 comes from.
Have you modeled any planets that are not in resonance?
No, I haven't.
Similar,
Right, no.
you know,
Mary, write that
not
down too.
exactly.
So other planets not in residence. Come on, Mary, write that down. Other planets not in residence, see what kind of patterns we get.
Well, it's actually Venus's, isn't it Venus's rotation? It's Venus's rotation that's.
On its axis, but that's not affecting this.
Right, yeah.
Orbit is still going the same way around the way we go. Same way around the racetrack.
But
So.
I'm sorry, it looks like even the larger petals are also 5.
Yeah.
Right.
If I count the larger petals,
Right.
they're
Yes.
also 5 as they.
Right. The next time I come, I will bring you a 7. I'll just go with the circular because that's easy. I'll bring you a 7 and 13 and just see if we get that same kind of lineup.
Use a faster computer.
Yes, that won't take 2 days to do it. Circular orbits are very easy, and the modern machines are much more swift.
It's also possible that on that one day when the Earth was supposedly blocking,
Right.
that the Martian might not have been able to see Venus anyway because it could have run from the sun.
It could have, exactly, and that's where I've got to try and figure out where were the planets at that moment in time. Mary's got that written down, so she's got it. We'll figure that out.
There's no quiz on this.
There is going to be a quiz. I'm a teacher. I've got to give a quiz. Okay. So, thank you very much. I love doing these little weird calculations. If you like this, I can do more little talks like these weird ones. But I pulled some of my better ones for this just because they're strange.
Well, we always have the short talks at Cranbrook.
Right.
So.
So is it possible for any planets to occult each other at any point?
Okay,
From
so
the perspective of Earth.
I'm going to go back to Gene Meas. Gene Meas puts out these amazing books. And one of his books, he gets Astronomy Morsels 1, 2, 3, 4, and so forth. So one of the books came out, and it's talked about the occultations of this is now blocking this planet, and it's doing the lineups not with the sun, but just these planets in a line, these planets in a line. And I said, oh, Earth, Venus, Mars, this will be perfect. He'll confirm my numbers. And he takes the numbers up to, so the calculations he does go up to the year 2600. Oh! Gee! Why? You could have took one more, 2 more decades, or 2 more centuries. You could have proven my numbers. So I'm looking through the chart. Earth, Mars, Venus, Earth, Mars. No, you stopped the chart. So, but there are a bunch of those. There's a bunch of those individual lineups of Earth and Jupiter and Saturn, and when does that happen again? When does that happen again? And so forth. Now he's got some great software because mine would take the 17 days to calculate when that is. So he's got some other way of doing that.
So any in our lifetime?
Oh yeah, plenty. I could bring some charts if you want. Just some. Here's these are going to be lined up in space. It's not with the sun,
right?
But it's that one there, that one there, that one there, forming a line in space.
So you might have to go to Jupiter.
Yeah, you have to go. Yeah, the travel funds. Well, we had a couple $100,000 in our budget, so the travel funds should cover that. So.
My question is, when I first saw your presentation, I was a little bit confused about. Now you're talking about the daytime on Mercury, way back to Mercury,
right?
As relative to what Mercury sees, technically, because the year is still, isn't it the rotational period, the revolutionary period of Mercury is 88 days,
right?
And the 59-day day, if you want,
right?
So actually,
that's a sidereal day.
Right. Okay.
So that's to the background stars. That's what Mary was doing with every time she moved to this spot, she faced a new. So that's sidereal. So it really would be if you were on Mercury, you would have your 24 your so high noon to high noon.
Right.
Is going to take 2 years and 3 rotations on the orbit to do it.
So in other words, because I always figured, Earth day is 24 hours and the year is 365. So
right.
Could you go back to that chart?
Oh, so in terms of Mercury days
relative to the sun
and Mercury years, yeah, you'd have to come up with a new name for it because now it's going to be a sol or something.
Oh, I got it.
Right.
Okay. All right.
Because I'm using Earth days just to get a reference frame.
I get it.
Yeah.
I get it. Yeah, that's good. Okay.
Could you go back to the chart that has the duration of the sidereal day versus it sort of shows the ratio between.
Oh, for the rotations on the axis? This one?
Yep.
Yeah.
Okay. So this axis period, this is rotation on the axis, that's sidereal. So we have Earth, now it's rounded here, let's see, wait. Yeah, so it's rounded to 1, but it's really, that's that 4-minute difference, right? Sidereally, we don't rotate. Here is the high noon for me. If I rotate on my axis and I go back to facing that wall, that's less than 24 hours. Right. If I then move a little bit more in my orbit and rotate a little bit more, boom, there's 24 hours exactly. So this is 23 hours and 56 minutes for the sidereal, to background stars. Right. To get to 24, I have to go back to here. Right, so that is sidereal for Mercury, and then going around is the A7. So it really would be a solar day, noon to noon. Right. Would take three rotations on your axis and 2 trips around the sun. Very weird.
I don't know how much you've done on Venus, but I've heard that the sun moves so slowly if you were on the surface of Venus that you can walk in the opposite direction fast enough to change the direction.
That's a great question. What Venus has, because Venus rotates the opposite way on its axis, so every half a year is 1 solar day for Venus. But I hadn't thought about how quickly you'd have to walk for the terminator, for where the light dark line is on Venus.
I hear it's slow enough that you can outpace it walking.
Nice. Okay, Gary, write that down. Can you outpace the shadow line on Venus? Outpace the shadow line on Venus.
Depends on your latitude. You can outpace the shadow line on Earth if you're in the North Pole.
Well, right. But Venus, we want to go to Venus and outpace it there. So you have to go, but this would be anywhere on Venus. You could anywhere along the shadow line.
Well,
no, not necessarily, because it's different speeds.
You're walking east or
west.
Right.
We have time for one more question.
Yes, and the discussion in the beginning, you're talking about adding these little increments of time.
Right.
Every once in a while, we hear about, because of the variations in the orbiting speed, they have to add a second or...
I cut out a slide. I had a slide on that, and I had to cut it for time. So
if they're able to do that now,
right,
and do it just about any time they want to, anytime they need to, don't we have the technology with the interconnectivity of everything that we could add these little leap amounts of time,
little tiny amounts
on every yearly basis as needed?
I think it's 16 times in the last 50 years or so they've added a leap second, because it's the rotation. Our moon is slowly moving away from us.
Yeah.
We're slowly rotating slower on our axis. Okay. And so we've got to make these adjustments. And you can we had the typhoon back in 2004 or so, that physically moved enough mass, just all the sludge in the mountain, tsunami. Sorry, that's what I meant. Tsunami. Yeah. That physically moved enough mass that we could tell the difference in the rotation rate of the Earth, because it changed the angular momentum, like a skater.
They could do it on a worldwide basis.
So now here's the thing though, you want to do it slowly, incremental changes. We have trouble with time zones in this country, and some cities don't even have the same time zone as everybody else in that same band.
Right.
You want the entire world to now incrementally make tiny changes over continuous time? I couldn't do it. Good luck. I applaud it, I like it, because then you don't have any of these rules, 4 years, 100 years, you don't have to remember any of that. And it's nobody else's problem if we do that. But you got to we can't even get St. Louis, isn't it St. Louis that's on their own time zone? No, who is it down south? Not
Arizona.
Well, Arizona, but there's a city, Indianapolis. Does Indianapolis have?
Indiana doesn't have it either.
Right. So there's
They changed.
They changed it. Okay, but we have problems with time zones even just in this country. There's only 3 time zones across the continental, and we have places that go, we don't really. Well, continental.
Right. No, Pacific, Mountain. Central,
sorry, right,
Eastern,
okay.
and Atlantic.
Physics, not math.
Atlantic.
But I think that's the real problem. Yes, with the interconnectedness of computers, if we have to go for this every 4,000 years, by then we've got to have our computer systems on a clock that can adjust these incrementally. So,
caves by then.
all right. Let's hope not. Don't say that. Don't say.
Didn't we just have a leap second recently?
I think there wasn't there a leap second?
Yeah. Last summer.
Yeah, I think they added one. Right, because we're slowing. We're all slowing down a little bit, right? I mean, each year, always slow down a little bit, so, okay.
And unfortunately, we are now out of time, so let's grab his first talk. Scott, I don't know if you're planning to join us at the Coney, but normally we go to the Coney Island at Van Dyke, just north of 12 Mile, to continue the discussion from here. Everybody's welcome to come. We put a bunch of tables
And I
together.
put the link out there that's got a whole bunch of other astronomy stuff, but if anybody needs that, if you saw my email, send me an email if you got questions, or I'll make sure the link gets out.
Okay. And Ken has one last announcement as we pack up.
As you're leaving, the Mercury